This integral, if we're going to do it with a limit and a summation, should become the limit as n approaches infinity of a sum from k equals 1 to n of f of x sub k, so 3x sub k squared, times our delta x value. And so what is our delta x value?
Two over n.
That'd be 2 over n. And what should our x sub k value be?
2k over n.
Just 2k over n, right? 0 plus 2k over n, since we're starting at a lower limit at a value of 0. Cool. So this gives us the limit as n approaches infinity of a sum from k equals 1 to n of 3 times 2k over n squared times 2 over n. Everybody good there? Which as we put all that together, we should get 2 times 2 times 2 times 3. So that should be 24k squared over n cubed, it would look like. And what's the summation? Should do this on a new page here, maybe. Oh, no. There we go. All right. That didn't do what I wanted it to do. There we go. What's the summation from k equals 1 to n of k squared? Anybody remember that one from the last time you did that? Sometime years ago, last year?
Isn't it n times n plus 1 times 2n plus 1?
It is in the numerator, and what's in the denominator?
Over 6.
Over 6. Good. All right. So we'll just go in and replace this k squared with that. That gets rid of our summation. So it's the limit as n approaches infinity of 24n times n plus 1 times 2n plus 1 over 6n cubed. And if we were to multiply all of that out, we note that this is a rational function with the degree of the numerator equal to the degree of the denominator. Both of them have a degree of 3. And so we'll just divide the leading coefficients. Leading coefficient in the numerator is 24 times 2, so 48 over the 6. And we just get 8 for that integral. Good or no?
Good.
Yeah,
All right. All right. Last one of these that we're going to do. You guys want to? No, let's just do this one together. We're running out of time. Well, not running out of time, but we're going to be short on time. So we'll do it. So what is delta x going to be for this one?
1 over n.
1 over n. And what is x sub k going to be?
1 plus 1 over n.
1 plus
1k, or k over n, sorry, my.
All right. 1 plus k over n. So we'll go and we will make this a limit as n approaches infinity of a sum from k equals 1 to n of 1 minus 6 times x sub k, which is 1 plus k over n squared, times delta x, or 1 over n. Good or no?
Good.
Great. All right. So simplifying all of that garbage inside of the brackets and all, notice the parentheses inside of the brackets there. Simplifying all that out, let's see here. So we got 1 plus k over n squared, which the first term is just going to be a 1, right? And then we're going to multiply that by 6, which is going to be 6. And we're going to do 1 minus 6, which is going to give us a negative 5. And that negative 5 is going to get multiplied by a 1 over n. So we're going to start with a negative 5 over n. And then we've got the middle two terms of 1 plus k over n squared is just going to be 2k over n. So that's going to become a minus 12k over n. And a minus 12k over n squared. Everybody good with that term?
Yeah.
And then the last one, the k over n times the k over n, within the 1 plus k over n squared is k squared over n squared. So minus 6k squared over n squared and minus 6k squared over n cubed as we distribute the 1 over n through it also. Everyone feel okay with that?
Yeah.
We'll just now evaluate the summation. So the summation of negative 5 over n times is just negative 5n over n. And the summation of the negative 12k over n squared is just n times n plus 1 over 2, with the negative 12 over n squared still there. And then the last one here is minus 6n times n plus 1 times 2n plus 1 over 6n cubed. And so we'll just, each of those is a rational function, so we can find each one by dividing the leading coefficients, since this one has a degree of 1, this one has a degree of 2, and this one has a degree of 3. This ought to give us negative 5 minus 6 minus 2, or negative 13. Good. Did somebody say something? I might have missed it if you did. Thought somebody said something.
No, that's good.
Everyone's good? Spectacular. All right, well then, in that case, let's keep moving forward. So that's the whole idea behind the integrals. This is what's happening behind the scenes when you just find the integral the nice, easy way that we'll start doing in a few minutes here. So before we start doing that, let's quickly talk about what's called the fundamental theorem of calculus. There's two parts to the fundamental theorem of calculus, and they sort of go hand in hand. The first part of the fundamental theorem of calculus says that the derivative of the integral of a function from a constant to x is just the function. So I'm gonna write that off to the side. The derivative of the integral of a function from a constant to x is just the function in terms of x. So effectively what that's saying is it's saying that the derivative and the integral are just opposite operations of each other, effectively. So that's why we call integrals antiderivatives sometimes. So we have a derivative and we have an antiderivative, and they are opposite operations of each other. So we're calling capital F the integral of some other function f from a constant to x. So the derivative of capital F is just the original function in terms of x. So think of them as opposite operations of each other, or inverse operations of each other. And as part of that, let's see, I think it's this one. Yeah, this will help us. We know that the second part of the fundamental theorem of calculus is that if you want to evaluate a definite integral, an integral from a to b of some function, it's just the function that is the integral of it, evaluated at the upper limit, b, minus the function that is the integral of it, evaluated at the lower limit of a. So the integral of little f of x dx is just its integral at b minus its integral at a, or capital F of b minus capital F of a. Hold on 1 second. Okay. Sorry about that. Kid across the street. My kid has recess from 10:15 to 10:45. So the kid across the street, or he goes across the street to see if that kid can like hang out outside and run around or whatever, but he never can. But he still goes and asks every day. And then at 10:45 he gets recess, but my kid's supposed to be back in class. So like then he shows up at the door. It's always, pretty much happens almost every day of the week. Good times. All right, so our definite integral just means we evaluate the integral of the function at b minus the integral of the function at a. Good or no? So that's the second part of the fundamental theorem of calculus. And we're going to sort of combine those two things together to figure out what these are. So these should be pretty straightforward for the most part. As we start to look at it here, we've got the derivative of an integral from a constant to x of some function. So what should that come out to be?
Cosine x.
Should just come out to be cosine x. And we suppose we wanted to write it out in a little more detailed way, and suppose we didn't know the integral of cosine. If we just said let capital F be the integral of cosine t dt, then the integral part would be capital F of x minus capital F of negative pi. And when we took the derivative of this, we'd get the derivative of capital F, which is just cosine. And then we'd get the derivative of capital F of negative pi, which is just the derivative of a number, which is just 0. Derivative of a constant is just 0. So if we wanted to write it all out, this is what we could say. But it's easy enough when it's just a constant x to say the derivative of that is just the original function in terms of x. So that's all we'll do from now on, even though when I post the answers to the assignment with the fundamental theorem of calculus, you'll see me write this kind of stuff out. It's not necessary to do. So what is the derivative with respect to x of an integral from 0 to x of 1 over 1 plus t squared dt?
One over 1 plus x squared.
It ought to just be 1 over 1 plus x squared. Easy enough. Good or no?
Yeah.
All right.
What would you do if the
Go ahead.
what would you do if the upper and lower limits were switched around? Would it be the same thing?
So we'll talk about that in a bit, but
Okay.
no. If the upper and the lower limits are switched around, you can flip them by taking the opposite of it. So you can always flip the limits of an integral and make it negative for one, or if you just go through this way and do it this way, suppose we were, I got one, let's see, let's do one of those right now. Here's one. Let's do this one first because this will answer your question. If we want to find the derivative of the integral from x to 5 of 3t sine t, well, and you don't know the integral of 3t sine t, I don't imagine offhand. We can say that capital F is the integral of 3t sine t dt. And so when we were to integrate this, we'd get capital F of 5 minus capital F of x, and then we'd be taking the derivative of that. And the derivative of this constant would be 0, so we'd have 0 minus the derivative of the integral of 3t sine t, which would just be 3x sine x. And so you'd end up with just the opposite of that function. Does that make sense?
Yeah, it does. Thank you.
Yeah, and so alternatively, we could also just say this is equal to the opposite of the derivative of the integral from 5x of 3t sine t dt. So you can also just flip the limits and put a negative out in front of it. That's one of the properties of integrals that we will eventually talk about. But yeah, then you'd end up with the same thing. Good or no?
Perfect.
Great. I wonder where I should have all those rules written in here, but I don't seem to have them, which is a problem. So I'm going to have to find those elsewhere and talk about it another day. All right, let's do another one. Now we no longer have the integral from 1 to x. We have the integral from 1 to a function. Right? And so we can think about this. I think it's a little easier to think about this in terms of what we were doing before, even if we don't know what the antiderivative of cosine is, which we should. We'll call f the antiderivative of cosine t dt. And so when I integrate 1 to x squared, that should give me capital F evaluated at x squared minus capital F evaluated at 1. So we're going to take the derivative with respect to x of that. And when I take the derivative with respect to x of a function at x squared, I have to use which rule?
The chain rule.
Chain rule. So that should give me the derivative of x squared, or 2x, times the derivative of capital F at x squared, which is cosine of x squared, and then minus 0. Good or no?
Yeah, that's chill.
That is chill. Wonderful. All right, so what should this next one then look like? Let's let f equal the integral of e to the t squared. So this becomes the derivative with respect to x of capital F of x squared again, minus capital F of 0, which should then become 2x times e to the x squared squared minus 0. All right, so we plug in the x squared for t, so it's x squared squared, and we end up with 2x e to the x to the 4th. Good or no?
Once again, quite chill.
Oh, good. I'm glad that it is quite chill. Anybody have any issues with that? Or we feel okay about that? All right. Now we already did this one, so let's skip on down to this one now. So this one gives us an integral from 2x to x squared of this function. So if we let capital F equal the integral of 1 over 2 plus e to the t dt, then this should be the derivative with respect to x of capital F of x squared minus capital F of 2x. Yeah? Once again, very, very chill there, I hope. And so when we take the derivative of capital F of x squared, that ought to be 2x times 1 over 2 plus e to the x squared, and then minus the derivative of 2x is 2 over 2 plus e to the 2x. Good or no?
Groovy.
Ooh, no longer chill. Now it's groovy.
It's also chill.
Oh, good. All right. Anybody have any questions on that? All right. Bear with me for 1 second here. I wanted to, maybe I didn't snap again here. Huh. All right. I thought I had all the rules, the properties of integrals in here. So I'm gonna have to find that, and we'll talk about those on Friday. But for now, we're just going to practice taking some very basic integrals. So the majority of you were in my class last year. You should know how to take all of these integrals already. For those of you that were not, I have posted up in the Google Drive and the other documents a list of all of the different integral rules that you should know. I'm not going to go through and like prove where each and every single one of them comes from. they all basically just come from doing the opposite of what we did with derivatives. And so we'll remember that anytime we take an integral that's just like a regular power, we'll use the power rule in reverse. So we'll go up from, let's say, from x cubed up to x to the fourth, and then we will divide by 4. So this becomes 2x to the fourth over 4, or x to the fourth over 2. And since it's an indefinite integral with no limits, we'll remember to put a plus c. Anytime you differentiate a constant, or sorry, anti-differentiate a constant, it just becomes the constant times the variable plus a c. And even for any of these non-whole number roots, or non-whole number roots, we can rewrite this as x to the negative 5 and integrate x to the negative 5. And so what would we get if we integrated x to the negative 5? We'd go up to negative 4 and divide by negative 4. So this would be x to the negative 4 over negative 4 plus a constant, or we could write it as negative 1 over 4x to the fourth plus a constant. So we're just using the power rule in reverse. This one's x to the 3/4, so we'll go up to x to the 7/4 and divide by 7/4, which will give us 4/7 x to the 7/4 plus a constant. Everybody good with those? We all remember how to do this? Or does it make sense for those of you that were not here in my class last year? You're going to want to look at that list of integral rules if you don't remember them all. Good or no?
Good.
All right. You guys finish this page off. I'll give you 2 or 3 minutes there to finish these last 5 integrals on this page. Ready, go.
Sine x.
Okay, just simplifies to an integral of sine x dx, and the integral of sine, if you don't remember it, it's on your sheet. What does that integral come out to be?
Negative cosine.
Negative cosine x plus your constant. All right, what about 5x cubed plus cosine x? That one ought to be 5/4 x to the fourth. And then the integral of cosine is
Sine x.
plus sine x plus rc. Good. What about this one right here?
Uh, 2t to the fourth minus 4t 3/2 minus 1 over 2t squared plus the constant.
All right. Sorry, I missed what you were saying because my child dropped cashews from the top of the refrigerator. What was the second term? Make sure.
Minus 4t to the 3/2.
Good, right? So t to the 1/2 up to the t to the 3/2. Just leave them on the counter. It's fine. Divide by the 3/2. So 4t to the 3/2, and then this one goes up to your -2. So plus what?
Wouldn't it be minus 1 over 2t squared?
Sure, minus 1 over 2t squared if we want to write it that way. Plus a constant. Everybody good there? What about the cosine cotangent one in the denominator?
That's just tangent secant. So
Yeah, that's the same as an integral of secant u tangent u du, which is just secant u plus your constant. And then what about this one? Let me give us a new page for that one. What was it? X squared minus 1 squared over x squared, right? How do we do this one?
Can't you distribute out the top and then divide everything by x squared?
That'd be perfect. So the top is x to the fourth minus 2x squared plus 1 over x squared. So anytime you have a single term, a polynomial, over a polynomial, but it's just a single term, just a monomial in the denominator, just divide them all. So this becomes the integral of x squared minus 2 plus x to the -2. And so that'll be x cubed over 3 minus 2x, and then minus 1 over x plus a constant. Good or no? All right. Do these four. Having you guys practice some of these nice easy ones today. So you got 4 of them right there. Ready, go. All right. So negative x to the negative 2 should just become what?
1 over x.
1 over x plus your constant. What about the next one?
Three-fifths x to the 5th plus 1 over x squared plus tan x plus c.
Good. Everybody okay with that one? Right. 3/5 x to the 5th up to negative 2. So you divide by negative 2. So it becomes plus 1. X to the negative 2 or 1 over x squared. Derivative of tangent is secant squared. So that one ought to be a tangent and then plus the c. What about this one? What is this one?
Arctangent plus c.
Yeah, that one's just inverse tangent or arctangent. Either way you want to write it. Inverse tangent u plus rc. And then integral of an e to the x is still just an e to the x. So 2e to the x plus a secant x. And then x to the 1/2 ought to become, that's a minus 2/3 x to the 3/2 plus our constant. Everybody good there or no?
Good.
Cool. All right. And what if we want to evaluate this with a definite integral? All we have to do is find the actual function, the integral x to the 4th over 4 plus x. And then instead of adding a plus c to it, we will just evaluate it from -1 to 3, which means we'll plug in 3 to the 4th over 4 plus 3 minus -1 to the 4th over 4 minus 1. And what does that give us? It gives us 81/4 plus 3 minus 1/4 plus 1. So what does that come out to be?
$24.
Comes out to be 24. Good or no? Any issues, any problems, any complaints there? Everyone's okay?
Good.
All right, you guys do this one. Then we got one more quick thing to talk about, and then we will be done for today. All right, ready, go. So what did you guys do first?
Expanded it.
So r squared plus 2r plus 1 dr. And then integrating to get r cubed over 3 using the power rule, plus r squared using the power rule, plus r using the power rule. From -1 to 1 ought to give us 1/3 plus 1 plus 1 minus -1/3 plus 1 minus 1. Second plus 1 minus 1 cancels, so we got 1/3 plus 1 plus 1 plus 1/3. Looks like that ought to be what?
8/3.
8/3 sounds good to me. All right, everybody feel okay about that? We can do definite integrals, we can do indefinite integrals, at least with the simple basic ones.
Yes.
All right. Then we're going to add one small last little thing here, and that is the mean value theorem for integrals. So the mean value theorem for integrals is a way to find the average value of a function on a closed interval from a to b. So effectively what we're doing is we are trying to find a height of this function that occurs somewhere between A and B, so that if I were to find the area of the rectangle made by a length of B minus A and a height of H, the area of that rectangle would be identical to the exact area underneath the curve from A to B. That generally make sense?
Yep.
Okay, cool. So on the left-hand side, the integral, the area underneath the curve from A to B, suppose this is just the function f of x, right? This should just be the integral from A to B of f of x, right? That's what the blue area is. And the red area ought to be the length between B minus A times H. And if we want H, we just divide by B minus A. And that gives us what we call the mean value theorem for definite integrals, that the average value of the function, or H or f of c, is equal to 1 over B minus A times the integral from A to B of our function. Good or no?
Yes, that's quite good.
Spectacular. All right.
It's
So,
not cool or groovy, but it's good.
okay. Well, good is better than not good. So, perfect. All right. Let's see if we can find the average value of 1 over x on the interval from e to 2e. So first off, what? What do we need to do first?
Verify it's continuous.
All right, we need to see if this function is continuous from e to 2e. So y equals 1 over x is continuous. That is a criteria we have here. It's continuous on the interval from e to 2e. Okay, right? So if f is continuous. We've done that. All right, we know that's true, right? 1 over x is only discontinuous at 0, and e to 2e doesn't include 0. So then we'll say this should be 1 over b minus a times the integral from a to b of 1 over x dx. And according to your sheet of integrals, what is the integral of 1 over x?
Natural log of x.
Log of x, and we'll evaluate that from e to 2e. So this becomes 1 over e times natural log 2e minus natural log e. And what's natural log of 2e? That's the same as natural log of 2 plus natural log of e. So we end up with an answer that is just natural log of 2 over e. And that is the average value. And if we want to know when does it obtain that average value, how we figure that out?
F of c is going to equal that value. So 1 over c is going to equal that.
Right. So we'll say this is right here. This is the average value, and I'll get a new page here. 1 over x equals natural log of 2 over e gives us an x value equals e over natural log of 2. So the average value is natural log of 2 over e, and it occurs at e over the natural log of 2. Any questions or issues there? Okay. People leaving left and right here today. Where's everybody going? We should still have a couple minutes left, right?
Yeah.
All right, that's what I thought. All right. What if I asked you to find a new function that was equal to the integral of some function with an initial condition? Right, these are called initial value problems. These are basic differential equations, for which we will have a full unit on differential equations eventually. But how would we figure this out? We'd say that h of x is equal to this integral, which is x cubed plus 5x plus some constant. And giving an initial value or an initial condition here tells us that we need to find the constant, right? So we'll say that h of 2, which is 2 cubed plus 5 times 2 plus c, needs to equal 3. And so we'll use that to solve for our constant. Our constant should be negative 15. And so h of x would be x cubed plus 5x minus 15. Good or no?
Good.
Wonderful. All right, you guys do one more of these. I think that's the last one. Yeah, that's the last one we're going to do today right here, number 30, page 37 here. So you guys do this initial value problem and then we'll be done. Ready, go. What's the integral of cosine?
Sine x plus c.
Sine x plus a c. F of pi over 2. Which ought to be sine of pi over 2 plus a constant. Needs to equal 3. What's the sine of pi over 2?
1.
1. So we got 1 plus c equals 3, or c equals 2. So we've got f of x equals sine x plus 2. And we want f of pi, which ought to be sine of pi plus 2. What's the sine of pi?
0.
0. So this ought to be just 2. Everybody good there?
Yeah, that's chill.